This is Unisa. My name is Annie, and our project is called Research. Just a quick recap, we classified for top clothing features in clothing tops. And we're going to start with a quick demo using a prototype website that we built. The database was populated using images that we didn't train on, and they were ran through our models to be stored in the database along with the labels. So for example, right now we're searching black long sleeve turtleneck top, and you can see that the results are as we intended. And then on the other side of the website, we have the manager side, where you can upload any images of your choosing, and then they will be first pre-processed and then run through each of our 4 CNNs, one for each type of clothing feature. And you can see that indeed, for example, the second one, it's a red, long sleeve, no button turtleneck top. And you can verify the other ones are correct as well. And so to give you more context, this is what happened when a couple months ago we searched black tight top on Urban Outfitters, a pretty popular online clothing store. You can see that clearly the results were not what we intended. And so we think this is a good issue to solve because so many people prefer to online shop these days. And as well, the manual labeling of inventory is very tedious and could be replaced with a classifier that generates more detailed, accurate, and standardized labels. And machine learning is actually a great application for this because the models will be able to adapt to the model's angles, postures in the photos, and as well, there's already a large availability of data online.
So in terms of the data acquisition process, this took a long time for us because we had to generate the entire data set from scratch. We did this by scraping over 20 online stores to get images based on a search engine result that we put in, and we used that automatically to classify it as the label. And then these are some statistics of the distributions of our data sets. We chose to have 4 separate data sets, one for each of the models, since it was easier for us to get like a specific feature from the search engine than trying to get images that like corresponded to all 4 features that we were looking for. In terms of the data pre-processing, we resized the images that we got and normalized them. We also horizontally mirrored them as part of data augmentation to get more data for classes that we were lacking in. And then here are some examples of the input images that we put into the model, and then the corresponding label tensors. So each tensor corresponds to one label that we put into one of the 4 classifiers. And then here's some pictures of the data set since we had to manually go through a lot of them. The main challenge during this process was that we found a lot of manual filtering had to occur because the results from search engines of online stores was so poor, hence the use case of our project as well. There was a lot of judgment calls that we had to make deciding whether certain pictures were too unclear. So like if the model wasn't in a way where you could see the classified feature, we had to remove those. And then we also wanted a really diverse and stylistically different data set so that our model can learn to generalize. So we had to scrape from a lot of different stores. So here's a screenshot of the database that we used for the customer side of the demo you saw in the beginning, which just has like the images that we put in and then the classified labels and the confidence scores. We also put some sort of like thresholding so that we had a certain amount of confidence that we wanted the model to have for us to classify it as that label. And then a general architectural overview of our project. So if you take an input image, we pre-process it, resize it, normalize it, and then pass it through each of our 4 CNNs, one for each feature, to get the corresponding tensor one-hotted output that we convert into, again, the like categorical feature and then store it into our database. So for each of our CNN models, they're slightly different, but the overall view is that they have convolutional layers with max pooling. We also did batch normalization and dropout layers, and then the fully connected layers with ReLU activation and some sort of output function.
So in order to optimize our model, we performed a hyperparameter grid search with these parameters. For example, we would decrease the kernel size when looking for buttons because they're so small in the image. And as well, we oftentimes increase the dropout to avoid overfitting. And this is our final optimized model, these. And so for example, you can see that for buttons, it took over 200,000 parameters to train, whereas for sleeves, it only took around 4,000, just to show how difficult certain ones were. And our final test accuracies are here. It ranges from 78% to 94% accuracy. And we're going to take a more detailed look starting with colors. On the left, you have the test confusion matrix. And you can see from the matrix that red and orange tend to get a little mixed up sometimes, which makes sense because they're similar colors. And with reference to the baseline, you can see the baseline performed roughly 42% accuracy, whereas our model performed 96% accuracy, which is a lot higher than the 15% random probability. And the next one is short sleeves. The short sleeves were a little bit more confused than the other because the range lied more or less in between sleeveless and long tops. And with reference to the baseline, you can see the baseline achieved 55% accuracy, whereas our model achieved 91% accuracy, again, much higher than the 33% random probability. And the next category is necklines. So because the necklines look kind of similar depending on the angle of the model, they were all a little bit more confused, which is why our model achieved 81% accuracy, whereas the baseline achieved roughly 35%. But this is still much higher than the 25% random probability. And finally, we have buttons, where there was a lot of false positives when it predicted buttons, yet there were none, and we'll talk talk about that in a sec. And then so for the baseline, it remained around random probability since it was binary at around 53%, whereas our model achieved 83%.
So a little bit of a reflection on our results. We found that we were actually pleasantly surprised with how well the model performed based on what we expected. The areas where there was confusion did sort of make sense to us, as like the confusion would be between colors that are very similar or like necklines that are kind of confusing to classify. And then in terms of the buttons, when we were looking at why we got so many false positives, we found that there was a lot of buttons on other aspects of the image. So for example, if the model had a pair of pants that had buttons, we also somehow ended up classifying those as well. So, and then in general, a reflection on the whole project. If we were to redo it differently, we might want to do a market survey to get a bit more research on what types of classes were popular in clothing features to make sure that our use cases were relevant and actually useful. We did run most of our stuff on GPU, but before that, we were running it on CPU, and it was so much slower. And then we also created hyperparameter grid search scripts, but we wish we did this from the start to eliminate how much manual kind of like work we had to do.
Fantastic. It's great to see. Great to see that last reflection. I'm not seeing everybody. I did ask this question. If you redid this from the beginning, something similar, how would you do differently? It's nice to see some thought on it. I really like this. It's really, really novel problem solving and diving into things and diving into what are sort of standard CNNs, but it's great to see how you tune each CNN, thinking about the problem. I think that's what a machine learning engineer begins to do. And so that's great. I don't have a question. I would like to see the demo at the beginning again, because I
There was actually more to, like there was 3 examples for each of the demos, but we just didn't have time.
Yeah.
We also wish we had time to show the live demo, but unfortunately we don't really have it.
So this is the manager side where you just upload any image you want, and then we pre-process them, run them through all of our classifier models that we saved, and then it'll give you the corresponding results.
Ignore the big blob that was because of
So
school
that-
recording.
Sorry, I can pause it there. If you could pause.
Okay, that's the classification output for the manager.
Yes.
The manager of the site. Okay.
And then for the customer side, you can search any sort of any of the keywords that we kind of looked for, and then it'll go into our database and try to find items that were classified with all of the entities that you searched. So,
for example, we haven't seen this one. I think this one is yellow. Oh, it's a little blurry on there. Yellow short sleeve. Yeah.
so and then we sort them based on the confidence score it got from our models. So we try to optimize for the most relevant pictures. So I think this is a red tank top, or like sleeveless tank.
And it does get the wrong location because of the limitations of our
Okay,
model.
I just want to see it up.
Yeah.
That's great. Wonderful. Mike.
What if I just type in shirt?
You will get everything that classified as a shirt.
Yeah, so I like the way we did the input it, we kind of took similar words. For example, like if you took button and button, you'll get the same result. And then if it doesn't belong, you will get like no.
So if you search a pink t-shirt that's short sleeve, you'll just get short sleeve because we didn't classify pink as a color. We forgot that pink was a color.
And just one comment, you said you'd like to use grid search for searching for hyperparameters. Random search typically does better. There's research backing that.
Thank you.
Great.